Thank you for watching this video. So in this video, we're doing question 7 of November 2023, question paper Physical Sciences, paper 1. And these are electrostatics. So I'll read question 7 statement and then answer the questions that follow. So let's go. Question 7. 2-point charges A and B, each with a charge of 3 times 10 to the power minus 9 coulombs, are stationary on a horizontal surface. Point P is R meters from A and 2 R meters from B, as shown in the diagram below. Let me try to read this thing again. 2-point charges A and B, each with a charge of 3 times 10 to the minus 9 coulomb, are stationary on a horizontal surface. Point P is R meters from charge A and 2 R meters from charge B, as shown in the diagram below. So what this statement is telling us, essentially what you can see here, we have 2-point charges A with this charge and B with this charge, right? So the charges are equal of these point charges, right? So there's a point P in between, such that this point is R meters from A. Here's the distance between P and A, and 2 R meters from charge B. That's what they're telling us. No problem. So 7.1. What are they saying at 7.1? They're saying describe an electric field. They want you to describe an electric field, right? It's more like, what is an electric field? Tell us what an electric field is. So I can just give a short, straight answer, or maybe try to explain it a bit. So let me try to explain it a bit and see how that goes. So let's say we have a charge here. Actually, let's say you have a charge. Here's this charge of yours. Let's say it is negatively charged, right? And let's divide here. Let's divide these two. These are two different scenarios. Let's say you have another charge here. Let's say this charge is positively charged. Here you have two charges. One is negatively charged and the other is positively charged. So if you have a charged particle or a charged sphere or a charged point, right? Each charged particle creates an electric field around it, which is what I'm going to define. So you might know that a negatively charged sphere around, if it's just sitting on its own, there's an electric field around it, which you might have drawn. A lot of them, they look like this. They are similar to this. And the field lines are going inside towards the charge itself. The electric field lines have this orientation. And a positive charge, you know, similar to this, if it's just sitting by itself, no problem. So try to make these as equal as possible. Make them as equal as possible. So these lines here that you see around this charged sphere represent an electric field. So these lines represent your electric field, which is what they want you to describe. But I'm not answering the question here. I haven't answered the question because I'm still explaining what an electric field is. Right? I'm going to explain what an electric field is. But so now I'm just preparing you so that you can go to that direction. So these are electric field lines. They represent the electric field, which is what I'm going to describe, or which is what I'm trying to describe. Even these ones, these lines that you see here, they represent your electric field. Right? No problem. So if this charge is sitting on itself with a negative charge, this is how the electric field line will look like. If the positive one is sitting on itself, this is how its electric field line will look like. So this line that I've drawn here is a divider just to show you that these two charges do not have access to each other. They're not sitting next to each other. That's what I'm trying to demonstrate by this barrier here that you can see. No problem. So, now, let's say now, we put another charge here. Let's make it negative, just because. Let's make it negative. So if we put another charge here, because both of them are negative, there will be a force between them, which is what kind of force? It will be repulsion. This small charge or this second charge or these two charges will repel each other because, like you know, that like charges repel, right? They will repel each other because these are like charges, so they will push each other away. Similar thing, if we can put maybe a positive one here, even these two will repel each other. They will push each other away because these are like charges. No problem. So, since we're saying these two charges, this big one and this one, the smaller one that I've drawn here, they are repelling each other, which means there will be a force experienced by this small charge due to that one. There will be force experienced by this charge because of this one. Similar, this one will also experience a force because of this one. Why is that? Because this one is also a charge, right? So it has its own electric field, which is similar to this one. So the electric field of this one and this one, they interact, then the charges will push each other away. Right? No problem. So this is what electric field you might want to think you would like. I would say think of like, or try to imagine it as like. I would say try to imagine an electric field as something similar to this. No problem. Which is a similar case to that as well. Fine, I'll move away. So now they want you to describe an electric field. So what is an electric field? So an electric field, right? Because I said that if you put this one here, it will experience a force due to that one. Right? So an electric field, it is an electrostatic force experienced, right, by 1 coulomb of charge, of this charge here. So it is not a force, but it measures the force experienced by 1 coulomb of charge due to this one. That's what an electric field is. Because you said this one will be repelled, which is to be pushed away. So now, the question is, how much is this one getting pushed by? How much force is this small charge feeling due to that big charge over there? Right? So, to measure that, you are measuring how much newtons of force will be exerted to each coulomb of this one. That's what an electric field is. It measures the electrostatic force experienced by 1 coulomb of charge. That's what an electrostatic force is, and an electric field is. That is what an electric field is. It's a measure of how much force is experienced by 1 coulomb of charge that is placed on an electric field at that point. Because you must be, it's important to be specific that the electric field, it is defined at a point, right? So if you can find how much how much force or how much newtons are experienced by 1 coulomb of this at this point, then every charge that you place there exact in that point, in an exact position, will experience exactly the same amount of newtons, which is the same amount of force. That's what an electric field is. That's what an electric field is, which is similar to this. So I won't do for both of them. I've done it for this, it also applies here. So what you have to do now is to describe or define what an electric field is. So let me not take 7.1 here. Let me not take 7.1, let me keep it as is and say 7.1. So let's go and describe an electric field. So it is important to note that an electric field, it is not a force. Because when I'm defining it, I'm saying electric field, it is the electrostatic force experienced by each column of charge at a point, right? So it's not a force, but it's a measure of how much force per column, how much force per unit charge at that point. That's what an electric field is. It's important to know that it's not a force. I would not want you to think as a force, but it's the magnitude of the force felt by each charge. Amount of newtons per column. That's what an electric field is. So, to describe it or define it, I'll say an electric field, right, is the electrostatic force experienced per unit charge at a point. There is it. So an electric field is an electrostatic force experienced per unit charge at that point, which means it is the magnitude of the force experienced by 1 coulomb of charge at that point. That's what an electric field is. It's a measure of how much for example, electric field is the electrostatic force per unit charge at that point, which means how much force experienced by 1 coulomb or per coulomb of charge at that point. That's how I would define an electric field. Done. So, we move to 7.2. What are they saying at 7.2? They are saying, draw the resultant electric field pattern due to charges A and B. So they want us to draw the electric field patterns due to charges A and B. No problem. So they want us to draw electric field pattern due to charges A and B. No problem. It should be similar to this. So we'll move now to 7.3. Okay, so now we're going to the next question, 7.3. So they're saying the magnitude of the net electric field at P is 27 newtons per coulomb. Let's read this again. The magnitude of the net electric field at P is 27 newtons per coulomb. So they're telling you at this point P here, the net electric field is 27 newtons per coulomb at that point P. Or maybe you can put P somewhere here. Let's say P is sitting somewhere there. It's closer to A than it is to B. No problem. So we're given the electric field at P, the net electric field at P to be this, 27 newtons per coulomb. Right? If we want to calculate the electric field at A, right? Or if we want to, okay. So, if we want to calculate the electric field at P due to A, it's going to be electric field at P due to A is equal to K Q of A all over R squared, right? This is the electric field at P due to A. The electric field at P due to B would be equal to K times the charge, B over R squared. This is how we are going to calculate the charges, the electric fields of both, this is how we are going to calculate the electric field at P due to both charges. No problem. So now, if we want the net electric field, the net electric field will be equal to E1 plus E2, which is electric field of P at P due to A and electric field at P due to B. So we just add the two. So it is important to keep in mind that an electric field is a vector, right? Because we are saying that it is a vector quantity, electric field, because you defined it as an electrostatic force experienced per unit charge. So it's the force experienced per unit charge. And you know that force is a vector. And this is the scalar, so the whole thing is a vector quantity. So, now, which is, what you do, you say, okay, your innet will be equal to what? K QA over R squared, right? Plus, let's say plus or minus K, which is the electric field of P due to A, which is these things that I'm writing here are those things that I've written there, which is plus or minus KQ of B, which is charge B over R squared. So now, what we're left to do is to decide the sign between the two things, right? Or assign the signs to these two guys. It's easier that way. Just assign the sign between these two guys. So let's go to this guy. So, if we're looking at P, let's look at P here. Let's look at P. P, if we can hide this and let's suppose that it's not there. Let's take it as if this thing is not here. If P is sitting here, right? The influence of these electric field lines, you can see that they are going outward, right? These electric field lines are going outwards, out of this one. If you are P here, you will be feeling electric field lines pushing you in that direction because they are coming out of A. If they are coming out of A and you are sitting here, so which means they are pushing you that way. So P will be feeling an electric field of at P due to A in that direction. So the electric field at that point at P due to A is in that direction, because if you take this as if it's not there, just imagine that it's not there, and look at the field lines of this. The field lines will be pushing this P away because they will be going out of this as they are doing here. So your P will be somewhere in a similar position as this one. So P will be feeling electric field in that direction due to A. And if we take A as it's not there and look at B alone, right? And look at B alone, you will see that now your P, if this is B, your P is in this side, is somewhere here. So the electric field experienced by at P due to B, because these field lines are going all directions, right? So the electric field at P due to B is pushing P to that direction. So each column of P will feel an electrostatic force pushing to that direction. So the electric field will be in this direction. No problem. So this is, some sort of vector diagram of the electric fields at P. This is a vector diagram representing electric fields at P due to A and B. Right? No problem. So, I said that An electric field is called the electrostatic force per unit charge. So, how do you find an electrostatic force? To find an electrostatic force, you use Coulomb, right? And say, okay, K Q1 Q over R squared, all divided by Q, right? So this and that go away. So your electric field is equal to what? K Q1, right? All over R squared. Very similar to Coulomb. So you can see that the magnitude of your electric field is directly proportional to the charge and inversely proportional to the square of the distance between them. So these two charges are identical because we both discovered that they are 3 times 10 to the power minus 9, both of them. But this point P is closer to this point P is closer to A than it is to B. And I just said that the electric field is inversely proportional to the square of the distance between the point of interest and the charge itself. So, and one thing that you should know, right? One thing that you should know, that the electric field strength is getting weaker as you move away from the charge. The closer you are to the charge, the stronger the electric field strength. But if you move away, the electric field gets weaker and weaker. So we can all agree that this point is closer to A than it is to B. So the stronger electric field at this point would be of A than that of B. Because the closer, in this case, these two are identical, so it's easy to compare, right? Because now both of them are identical, they have this charge. So they have, I'll say, equal electric field strengths, both of them. But now, because P is close to A, there's a stronger electric field. There's a stronger electric field at A due to there's a stronger electric field at P due to A than that due at B, because B is a bit further. So the electric fields are a bit weak. This electric field influence or lines are a bit weaker here at P. So if they are saying now the electric field, the net electric field at P is equal to 27, right? I would think that this one, which means this one here, is the electric field at P due to B, right? So I would think this one is the one that is stronger. I'll say this is the dominating one. Because these ones are closer, or P is closer to A than it is to B. So there's a stronger dominance of the electric field of A than that of B. So in that case, I would like to say that at P, the net electric field is to the right because of the stronger dominance of the electric field of A. Because that of B is a bit smaller because there's a bigger distance or greater distance between P and B, right? So what do we do? So, you assign your coordinate system, or you decide your directions. So I was saying, this one is positive, the electric field to that direction is positive, and this one is negative, right? So which means I will have this electric field positive and this one negative. And because I think my electric field its net electric field is to the right because charge A is dominating B, then the net will also be positive. So what I will have is positive 27 newtons per coulomb is equal to K, which is 9 times 10 to the 9, times the charge of A, which is 3 times 10 to the power 9. All over, the distance between A and P is R, so all over R all squared. Minus K, which is 9 times 10 to the 9 times the charge. What is the charge? The charge is 3, this is negative 9. It's 3 times 10 to the power minus 9. all over 2r all squared. So the 27 is equal to what? 9 times 10 to the 9 to 3 times 10 to the minus 9 all over r squared minus 9 times 10 to the 9, 3 times 10 to the minus 9 all over 4 r squared. So from here, if you want to solve for r, you can use your own solving abilities to solve this situation. So you know how to solve this. You've done quadratic equations at grade 11, since grade 11. And I will assume that when you write paper 1, you solve quadratic equations as well. Because these were very common at grade 11. At grade 12, they don't ask them a lot, but you know how to solve this. So what will I do? I'll say, okay, I'll take out common factors, right? I'll say, okay, 27 is equal, you don't have to solve my way. This common factor, this common factor, you can see this, and this is also, take it out as a common factor too. So here, actually no, oh actually I will. So I'll say 9 times 10 to the power 9 times what? 3 times 10 to the power negative 9. What am I left with? So I'll take r squared as a common factor as well at the bottom. R squared. And then here I'm left with 1 over 1 minus 1 over 4. Right? So 27 is equal to, so you can see that this and that will make up 1. So left with 27 over r squared into what? Into this, which is this time that is 4 minus 1 over 4. So you are left with 27 is equal to 27 over r squared is 3 over 4. No problem. So divide by 27 both sides. We are left with 1 is equal to 3 over 4 r squared. Cross multiply, you get that 4r squared is equal to 3. Then what do we do? Divide by 4, divide by 4. You get that your r squared, because this and that go away, is equal to 3 over 4. Then take the square roots to the square root. So your r is equal to square root 3 over 2. So therefore your r is equal to, punch that in the calculator and see what you get. So you have the square root of 3 over 4. You get that this is 0.87 meters. Okay, so now we're doing 7.4. 7.4 reads as follows. Calculate the magnitude of the net electrostatic force that an electron would experience if placed at point P. So they're saying, if we had at P an electron here, exactly where P was sitting, which is that distance away from A, what would be an electrostatic force experienced by that electron? So you know that electric field is equal to the electrostatic force experienced by unit charge, right? But in this case, you want to find the electrostatic force, right, experienced by a unit charge of an electron. Right? This is what we want to discover. So, what do we say? Say our electric field, our net electric field is what? 27 is equal to the electrostatic force per unit charge, which is what? Electrostatic force, which is what we want, per unit charge, which is 1.6 times 10 to the power minus 90 coulombs. Right? So your force is equal to cross multiply. So we have a 27 times 1.6 times 10 to the power 90 coulombs, which is your electrostatic force that will be experienced. Your electrostatic force that will be experienced by 1 coulomb of charge. Actually, the electrostatic force experienced by an electron at that point will be 7 times 1.6 times 10 to the power minus 19 is equal to 4.32 times 10 to the power minus 18 newtons. So this is the magnitude of the net electrostatic force that will be experienced by an electron that is placed at the point where P is sitting, which is 0.87 meters from A. So it will experience this magnitude of force down here. So I would like to say we're done with this question. So we'll move to the next one. Thank you for watching. I hope this does make sense to you as it does to me. Cheers.